Welcome to BKW Physics. My name is Mr. McConnelly, and today we're going to talk about friction. I'm going to start out by going through a few slides on a PowerPoint, and then we're going to move to an example that I will show on the board. I want you to imagine, start out this lesson, imagine if there were no friction whatsoever. If there were no friction in the world, what would things be like? Could you walk? Could you do just about anything? Think about all the things that require friction. In order to stand, you got to have some friction. Okay? In order to write with your pencil, you have to have some friction. In order to fly, you need friction. Okay? To drive a car, you need friction. You need friction for almost every situation. So, a world without friction would not work too well. As a definition, the force that opposes the motion between two surfaces that are in contact. The force parallel to the surface and in the direction that opposes the slipping of the two surfaces. So it's kind of tricky to put a definition on friction, but basically what we're saying is whenever you try to move something, friction will oppose that motion. It's parallel to the surface, and it's opposite the direction you're trying to move. So if I try to take off running this way, then my friction must be the other way. That way. All right? That's the basic definition. Static friction. Static friction is one particular type of friction. So what we're going to see is that friction can be broken into two categories. The first category is static. And what static means is that you're opposing the start of motion. So when I go to take off on a race, and I take off like in a running race, that's static friction because my feet weren't moving until the gun went off and it was time to run. So if you're starting motion, it's static friction. The other type of friction is called kinetic or sliding friction. Now this opposes motion again, but it opposes motion on two objects that are already moving relative to one another. So if I have a textbook, and I know you can't see it on the video, but if I'm sliding a textbook across the table, that's kinetic friction. The two surfaces, the book and the table, are sliding past one another. That would be an example of sliding or kinetic friction. So underneath that, I have a question. I pose a question. Will a car stop faster by not locking the brakes or by skidding? So what I mean by this question is, any car that's a more modern car from the early 90s, we'll say, all the way up to a current car, has this thing that is standard, and it's called anti-lock brakes. Now what anti-lock brakes do is when you slam on the brake pedal because you have to stop under an emergency situation, if you slammed on the brake pedal and you didn't have anti-lock brakes, the tires would just stop rotating. So you'd be going down the road and your tires would be not moving, and all your tires would be going across the asphalt. But new cars, or newer cars, have anti-lock brakes. So if you slam on the brakes and you try to stop really quick, the computer does this thing where it says, uh-oh, the wheels are starting to slide. And it lets off the brake, and it allows the wheel to turn, and then it hits the brake again, and when the wheel starts to slide again, it lets off the brake a little bit. And you can't override that. You can't control that. When your foot is pushing hard on the brakes are actually turning on, turning off, turning on, turning off, but it's happening very quickly. Okay? And so anti-lock brakes make it so that your tires aren't sliding. So my question, again, will the car stop faster by not locking the brakes or by skidding? And what's the answer?
Not locking the brakes.
Why is that?
More connection with the ground.
Which goes back up to static. Static is a larger friction. It's the larger of the two frictions. So if it's the larger of two frictions, and you can stay in that situation longer, anti-lock brakes allow you to use more static friction and less kinetic friction. Now you gotta stop quicker. So it's been proven by many scientists, oops, went too far. It's been proven by many scientists that anti-lock brakes always are going to allow you to stop quicker. And since that's true, they made it a law, they put it on all the cars. Okay, moving on. That's basically what I was saying here. The force of kinetic friction is less than static friction. So you want to, if you're trying to stop quick, you want to stay with the static friction as much as you possibly can. And that's what the anti-lock brakes do for you. They don't allow you to slide. All right, other question. Down at the bottom here. Is it harder to start something moving or to keep it moving? So you got a huge box and it's too heavy to pick up. And you're just going to, well, I'll just slide it across the floor because it's in my way right now. So what happens? You go, you're pushing on this box. The box will begin to slide. And when it begins to slide, is it easier or is it harder? What's your opinion?
Easier.
Easier. You know that. Once you get something moving, it's easier to keep it moving. Correct? That's the idea, again, between static and kinetic friction. Okay? You had to use static to get it going. That's the big one. And once you got it going, you drop down to kinetic, which is a less number, a lower number. Hi?
Sounds good to me.
Awesome. So there's an equation that ties this all together. FF is mu Fn. Now I know I wrote U, but I just couldn't figure out on the computer how to make a mu. I'm sure it's in one of the menus. But a mu is with two tails. For the people in my room, you can look up on the sideboard. It's right above opportunity poster. Mu. That's what it's supposed to be right there, a lowercase u, mu. Okay, so the equation basically says this. FF is the force of friction. It can be kinetic or static. It'll work for either situation here. Any force is in units of, everybody?
Newtons.
Thank you, newtons. Coefficients, well, you're not really familiar with these yet, but this particular coefficient is the coefficient of friction. And what it is it's a number that we have previously placed on a situation. Let me give a more detail. If you try to slide a rubber tire across asphalt, because that was our example earlier, is that easy to do? Rubber and asphalt, are they sticky towards one another or are they slidey on one another?
Sticky.
They're sticky. That would give you a certain mu value. In comparison, what if I took the same rubber tire and I tried to slide it on a sheet of ice, like on a pond? Would that be sticky or slidey?
Slide.
Slidey. So in comparison, the rubber tire on the asphalt would have a higher number than the rubber tire on the ice. That's what a coefficient is. It's a number that compares how slippery two surfaces are to one another. Okay? And actually, we'll go there in a minute, but in your earth science reference tables, there's a whole list of values for coefficients. These coefficients are found on the front page, and there's ones for kinetic, and there's ones for static. So you can look them up when you need them. And the last thing that I have defined here is the Fn, which we learned previously is called the normal force. And it's always equal to the force of gravity when you're on a flat ground. Like if you're sitting on your chair right now, the force of gravity is down, but you're not falling down, so the normal force is up, and those two forces are equal and opposite, and they cancel out. And since it's a force, it's in newtons. Now, let's look at a situation where you have a textbook, like I said earlier, that's being pushed across the table. That blue blob is supposed to represent a textbook. Fine. The blue blob, the textbook, is going to be moving to the right. Fine. So if I were to draw my force arrows on there, I would say that I'm pushing it to the right, so there's an applied force, APP, applied force that way. But friction is always slowing me down, it's always dragging. So that would be to the left, because if the book's trying to go this way, then friction is the opposite way. The book has weight, so it's pushing down, but the table is holding the book up, so that's the normal force. And now I could ask the question, well, how might I set up a situation where I can solve for the applied force? So I can solve for this force. How might I set that up? And at this point, I'm going to switch over to writing on the whiteboard. And what I'm going to do here is I'm going to go back to our picture again. Now our picture was this textbook that was being pushed. It has an applied force going this way, it's got a frictional force going this way, it's got a normal force this way, and it's got a gravity force this way. So how might I solve for the applied force? Well, what I could do was this. And this is the situation, this is the scenario that I always do. I say the net force is equal to all these forces added up. So friction, applied, normal, and gravity. And I'm trying to solve for that one. But I can cross out two of them right away, because the normal force and the gravity force are equal and opposite. If this is 10 up, this is 10 down, they cancel each other out. They're gone. You can just get rid of them. That makes it kind of handy because it kind of simplifies things. So I've crossed out two of them. And we also learned a moment ago that the force of friction was the same as mu times Fn. Remember when we just learned that a couple slides back? And we know from a couple days ago that the net force is the same as mass times acceleration. So I haven't given you any numbers. I did that purposely. I'm trying to give you the general picture. The general picture is, if I were trying to solve for the applied force, I might be given the force of friction, but I might also have the mu value and the normal force. And I might be given the net force, but I might also just have the mass and the acceleration. See, I have options. I have different scenarios. And there's one more scenario I want to add to this for today, is remember I said in the one slide that the normal force was the same as the force of gravity when you're on flat ground. Remember that? And if that's true, what do we know about the force of gravity? What is that equal to? That's acceleration of gravity. You're close. It's mass times gravity. So it's what you said, Stephanie, 9.81, but it's times mass. Okay? And when you multiply those together, it gives you the force of gravity. So now you can see that we have a variety of different ways that we can attack this problem, and without any numbers, I have a lot of different things that could possibly happen here. So for today, that's it. Physics.